All right, ladies and gentlemen, we are back and better than ever. Today we are going to be diving into 10.3, which is all about chords. Now remember, a chord of a circle is a segment whose endpoints are on the circle. And so there are actually a handful of theorems that we can utilize using these chords. The goal of this entire section is to be able to use chords to find lengths and arc measures. Today we are going to dive on into what we call the congruent corresponding chords theorem, the perpendicular chord bisector theorem, and the perpendicular chord bisector converse. It seems like a lot. Good news is you can rewatch this video as many times as you want until it kind of sets in, all right? But the reality is it's not that complicated. It'll just take some time to let it simmer a little bit. So let's dive on in to our first theorem, and that is our congruent corresponding chords theorem here. Now the good news is that these are kind of what I call common sense theorems for the most part, which ultimately says that if you have two congruent chords, like you see in this example here, AB and DC, these are congruent chords. The segments in and of themselves are equal in length. The only way that these guys are congruent is if the subtended arcs, right, the corresponding arcs CD and BA are also congruent in length. So if the length of the chord is congruent to this length of this chord, that means the length of the arc and the length of the arc are also congruent to one another. So let's go ahead and take a look at an example of how we can utilize this first and foremost. So it says that in the diagram, circle P is congruent to circle Q. It says that arc FG is congruent to chord JK. And so if that is the case, what ends up happening is that we have congruent arcs as well. Now, if, for instance, okay, this was not a congruent circle, we could not utilize our congruent corresponding chords theorem. Notice it says in the same circle or in congruent circles, okay? So the fact that these two are congruent circles and JK and GF are congruent chords, it tells me that arc GF is congruent to arc JK. And so if the two arcs are congruent, we can say that the measures of them are also going to be equal to one another. And so that means that if JK equals 80 degrees, so does the measure of GF. And so in its most simplest context, that's how we utilize this theorem here. Now, of course, ultimately, we can make it a little bit more intense in the end. So before we get into this example, let's take a look at one more theorem and its converse, and that is called our perpendicular chord bisector theorem. Perpendicular chord bisector theorem. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and the arc, okay? So what this tells us here is that EG is a diameter. We know this because it goes through the center of the circle. If it's a diameter, it is going to intersect a chord and be perpendicular to it. If this does happen, it actually bisects the chord and bisects the arc as well. So FH and HD are congruent, as are arc FG and arc GD. So it creates two different pairs of congruency based on its theorem. And we also have a converse, so it works backwards. So let's say, for instance, you see that a chord is being bisected and is perpendicular. That's enough to prove that the intersecting chord is the diameter of the circle. So basically, we can use this when saying like, hey, like, here's some information we have. Maybe we want to find the measures of arcs, and it will now allow us to show, for example, that SQ is a diameter, therefore arc SQ is a semicircle. So that's how we can kind of utilize these things in some application. So let's take a look here at finding the lengths of HK and arc HK as well. So let's take a look. What do we know? Well, we know for sure that LJ is a diameter. Reason being is because it goes through the center of the circle. It is perpendicular to chord HK. So if that's the case, I can prove that HK, right, is actually made up of HN and NK, HN and NK. So therefore, HN is congruent to NK. Therefore, HN has a measure of 7 as well. And we know that HK is HN plus NK. That means that the entire value of HK, of course, is then going to be 14. All right, so that's how we can finalize the identities of and the values of certain chords and parts of the chords using this. And of course, if they gave you expressions, you can set things equal to each other. Maybe they use a segment addition postulate in the process. A lot of different options there. Let's finish up this idea, though, and find the measure of arc HK, though. Now be careful, this is not a semicircle because it does not go through the center of the circle. And so since this is the diameter and HN and NK are congruent, it means that arc HJ and arc JK are also congruent. So that means that their measures are equal to one another. So I can solve and get 10x equals 70, and x has a value of 10, nope, of 7, of 7. Therefore, I can go ahead and find the value of the entire arc HK by substituting x back in to each of their respective spots, or since they are congruent to each other, of course, you can just go ahead, substitute it into one guy, and then multiply by 2. And so we get 77 here, and we get 77 here. And so then ultimately we get, what, 140 plus another 14. So that means the measure of the arc HK would have a measure of 154 degrees. So that is how we can utilize both our perpendicular chord bisector theorem, its converse, and our congruent corresponding chords theorem.